Hello everyone and welcome to the presentation of the poster named Graph Neural Networks for Investigating Complex Diseases, a case study on Parkinson's disease. My name is Elisa Gómez de Lope and I'm presenting the poster on behalf of myself and my co-authors Ramon Viñas-Torné and Pietro Leo from the University of Cambridge and Enrico Glab on behalf of the NICE Therapeutic Consortium in the University of Luxembourg Biomedical Data Science Group, where I myself am a PhD student. This is a poster presentation for the 31st Annual Intelligent Systems for Molecular Biology Conference and the 22nd Annual European Conference on Computational Biology. That said, let's go and start with an introduction to the topic. Omics data analysis is a critical component in the study of complex diseases. But the high dimension and heterogeneity of data often pose challenges that are difficult to address by classical machine learning methods. Recently, structured data analysis using graph neural networks, or in short GNNs, have emerged as a promising complementary approach, particularly for investigating the relational information between samples. However, it is still unclear which strategies for designing and optimizing GNNs are most effective when working with real-world data from complex disorders, such as Parkinson's disease. Our study addresses this gap by examining the application of various GNN models, including Graph Convolutional Network, ChebyNet, and Graph Attention Network, to identify and interpret discriminative patterns between PD patients and controls using two independent omics datasets, transcriptomics data from PPMI cohort and metabolomics data from the Luxembourg Parkinson study. Here I show a schema of how I generate a sample-sample similarity network. Starting from abundance omics metrics, we apply the feature selection based on lasso penalty and data scaling, so we obtain a more concise and compact omics matrix representation. From there, we generate a similarity matrix using cosine distance, and then we remove self-loops, we apply a similarity threshold and add edges between unconnected nodes because we want all samples, so all individuals, to be connected somehow in the network, even if it is with weak edges. So we get an outcome, like a diagnostic outcome for each sample. Like I mentioned, the pipeline was trained and evaluated in an end-to-end manner in two independent PD omics datasets and these three graph representation learning models. A thorough hyperparameter optimization was done in cross-validation using random search, and an experiment model was also added to the pipeline to gain insight and interpretability on the model's decisions. So, for each of the 10-fold cross-validation, 130 runs were launched exploring different values of regularization penalty, similarity edge threshold, learning rate, weight decay dropout, number of convolutional layer units, and K parameter for the ChebyNet model. Despite some variability in these visuals, you can see that some trends are evident. The best models, so those with a lower validation loss, or here lighter yellowish color, tend to be achieved when avoiding higher learning rates in combination with lower weight decay and dropout rates. So we see that these lines tend to be a bit darker, so higher mean validation loss, which we want to kind of avoid. In terms of results and conclusion, we see that in this implementation, the attention mechanisms in GATS did not provide advantages when compared to GCN and ChebyNet, while ChebyNet performed better than GCN. However, contrary to previous research on graph classification tasks, using a GCN layer did not beat the more established methods that only take a flattened representation into account. For example, here we compared the graph representation learning methods with a support vector machine using a right kernel, so no graph structure, and we see that this method obtains a higher performance metrics on both datasets than the graph representation learning one. We hypothesize that the reasons may be a high level of noise combined with limited sample size that is hindering graph convolutional operators from learning meaningful representation that allows to distinguish PD patients and controls. And we hypothesize as well that incorporating molecular interaction network or multi-omics data sets, so multi-omics data from the same cohort rather than single omics from different cohorts, or just different embedding approaches like autoencoders may allow more research, may allow our research node embedding setting. And then last but not least, I wanted to show the metabolites that were found as most frequently appearing in the top 20 most relevant features for tenfold cross-validation CheViNet model using a subset of unmedicated de novo PD patients versus controls from the metabolomics cohort. Using this subset of de novo patients is important because that way we get rid of the treatment effect. Interestingly, we saw some features that have been already associated with Parkinson's, for example, carnitine and benzoyl carnitine and purine nucleotides from a purine metabolism containing xanthine insulin in this case, and also nucleotides from the purine metabolism. So this is relevant because that helps us gain insight and avoid the black box typical setting. Now let me end the presentation thanking the funding agencies, and please don't hesitate to drop me a line or reach out in next week in Lyon. I hope you enjoyed the presentation. Bye!